Hello and welcome. This is the Taming Wild AI channel, where we bring AI technologies out of the wild using the best practices of software engineering. Today we're going to look at a deep neural network model called AlexNet. This was introduced in a 2012 paper entitled ImageNet Classification with Deep Convolutional Neural Networks by Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton. Here is a diagram of the AlexNet network. Note that this diagram reflects the distribution of these layers across two GPUs. This network is more complex than the previous network we looked at, AlexNet, and they trained it on a much larger data set. We trained AlexNet on MNIST. MNIST consists of 60,000 training images and 10,000 testing images, each 28 by 28 grayscale pixels corresponding to 10 categories, one for each digit. AlexNet made an enormous impact on modern artificial intelligence by classifying ImageNet images with high accuracy. ImageNet consists of 14 million images of varying size and resolution corresponding to almost 22,000 categories. The categories are usually words like strawberry or balloon, depending on which objects are present in the image. A subset of this database has been used in competition between AI researchers. You can download it from Kaggle after accepting the rules of the competition. But even the subset consumes about 150 gigabytes of disk space. If we want to train a model using this dataset, we need to be prepared to spend a lot of time and disk space just to download it, not to mention the actual training time. Now, when a paper presents a technology, one great resource for finding an implementation is papers with code. If we search for AlexNet and click on the title of the paper, we see an official implementation. This is something like an IPython notebook. But there is also an implementation inside the PyTorch framework repository. This is very promising because it looks like the PyTorch maintainers have brought AlexNet and several other models in from the wild. In fact, they offer these models pre-trained on the ImageNet subset. This is all part of the Torchvision library. We can look at their source code for AlexNet and see that it corresponds to the paper. The paper says the first 5 layers are convolutional and the remaining 3 are fully connected. I do notice here that the layer configuration values are hard-coded according to the paper. This means if we want to experiment with variations on AlexNet, we'll have to subclass the AlexNet class or replace it entirely. The paper says the output of the last fully connected layer is fed to a 1000-way softmax, which produces a distribution over the 1000 class labels. It's good that the number of classes is a parameter of the model, so we could train it on a dataset with a different number of classes. It looks like the Torchvision library expects us to put the output through a softmax ourselves, as this example shows. At the bottom of this file, we see some code to support loading weights to give us a pre-trained model. Unfortunately, there is no training code provided. So if we want to do any training, we would have to provide a loss function, an optimization method, and a training loop ourselves. Now, it's good to have a freely available model and the option to have it pre-trained, but in real life, a freely available pre-trained model may be too much or too little for our needs. We may need to train the model from scratch on our own data set. One important reason for needing to do this is that the pre-trained model might be subject to license terms and conditions that are derived from the training data set. While training on our own data set, we might need to experiment with hyperparameters, or we may want to do transfer learning, where we freeze input layers from the pre-trained model and train different output layers on our own data set. Let's see what's involved in doing this using this PyTorch implementation of AlexNet. Alright, I'm here in VS Code with an empty directory called AlexNet. I'll create a virtual environment and install PyTorch and Torchvision in it. Let's create a requirements.txt file and put the two dependencies in it. And let's create a README file with copy and paste instructions for installing the dependencies. Yep, that works. If we want to train on our own data set, we should start with a small, simple one. So let's start with a test to train AlexNet on the MNIST dataset. We'll create a tests directory and add a file called fulltraining.py. Now, in the last episode, we trained the LeNet 5 model on MNIST, and we put the dataset code in its own class. Let's reuse that class here. I'll create a dataset.py file and paste that code in. And in fact, let's paste the code that trained the LeNet model too. Of course, we will replace LeNet 5 with AlexNet. And we'll specify that we are classifying 10 classes instead of the default, which is at 1000. And for now, I also want to print some progress instead of just testing silently. All right, now let's see if that works. Our code downloaded the dataset, but it's no surprise that the test failed because we haven't implemented the training methods on the AlexNet class. Let's create a local subclass of AlexNet and add the training and testing methods that we previously implemented on LeNet 5.
Let the code flow.
I added this local subclass that derives from the Torchvision implementation of AlexNet. I made sure that my initializer calls the AlexNet initializer. I added my training and testing methods to my subclass. What's happening now is that AlexNet is architected to classify full color images with 3 channels of data for red, green, and blue. That's why the first layer of AlexNet specifies 3 input channels, but MNIST has a single grayscale channel. So after constructing the standard AlexNet network, I'll replace the first layer with one that has the number of channels I want.
Let the code flow.
I added a parameter to my subclass of AlexNet to specify the number of input channels. I don't particularly like creating the network in the superclass and then replacing one of its layers here, but the alternative would be not to call the superclass init method at all and instead duplicate most of its code here. In the test for MNIST, I'm passing the number 1 for the single grayscale channel MNIST uses. The problem I'm running into now is that MNIST images at 28 by 28 pixels are just too small. Convolutional and pooling layers transform an entire region of the image into a single output. They tend to shrink the input. For this reason, a small input simply can't be processed by multiple convolutional and pooling layers. Fortunately, our dataset pre-processing code already includes a transformation to resize the input. So I'll simply increase the size of the image presented to the network. Our code is working, but I'm noticing a data science problem. The loss level seems to be stuck. This commonly happens if the learning rate is too high. Let's cut our learning rate to 1/10 of what it was and see what happens. Our test passed, but it took 76 minutes to train. As I hinted earlier, if you do have a pre-trained model and you're able to use it, then there are a couple of ways to speed up the training. One is simply to continue training the same set of weights exactly as was done originally, just now with your dataset. You can do this if your dataset is of the same format as the original one with the same set of class labels. This is sometimes called fine-tuning. Because the model is pre-trained for another dataset, it converges on your dataset more quickly than it would from scratch. Another way to speed up training is to freeze the input layers of the pre-trained model and retrain different output layers from scratch. You need to do this if your dataset has a different set of class labels from the original one. This is sometimes called transfer learning. Not only does such a model benefit from layers trained on the original dataset, but it now trains only the weights in the output layers, so it converges on your dataset far more quickly than it would from scratch. Because the MNIST dataset is single channel or grayscale, it's dramatically different from ImageNet, which is full color, so we can't easily fine-tune or transfer learn from an AlexNet model pre-trained on ImageNet. The CFAR10 dataset, on the other hand, is full color, but still more manageable than ImageNet. It consists of 60,000 32 by 32 pixel color images in 10 classes. Let's modify the dataset class to accommodate training and testing with the CFAR10 dataset.
Let the code flow.
What I did here was create two different methods. One for CFAR10 and one for MNIST. Both methods initialize the training set loader, the testing set loader, and the length of the testing set. The user of the class passes the name of the test set into the init function, and from this hash map, the init function calls the appropriate initialization method. This generalizes the class, so I can add new data sets in the future by adding an initialization method and an entry into the hash map. If the user passes a name that's not in the map, then the init method will throw an exception that's probably reasonable for now. Behind the scenes, I created git commits before and after these changes. Now let's use this modified class in our MNIST test. And let's add an almost identical test for CFAR10. We can run this test as follows. That seems to be working. All right, the training code is working, but the accuracy was only about 75% at the end of training. I spent the last several days looking for a reasonable test of convergence on this CFAR10 dataset. I tried a couple of different optimizers, they didn't work. Then I looked back at the paper. The paper says we trained our models using stochastic gradient descent with a batch size of 128 examples, momentum of 0.9, and weight decay of 0.0005. So I replaced the optimizer that I was previously using with this one. I also changed the batch size of my CFAR10 dataset to 128, but the model still would not converge. The paper also says the heuristic which we followed was to divide the learning rate by 10. The learning rate was initialized at 0.01 and reduced 3 times prior to termination. So I added a learning rate scheduler to multiply the learning rate by 0.1 at the end of 3 epochs during the training. I still wasn't getting 99% accuracy the way I was with MNIST. The paper trained for 90 epochs and reported 84.7% accuracy on the ImageNet dataset. Unfortunately, I could only get to 81.7% accuracy on CFAR10. So if I want this test to pass, I would have to make this change. Or maybe more like that. Now, training from scratch for 90 epochs takes about 9 hours. Another problem I ran into was that for some reason, after executing the test to completion, my system would freeze for a few minutes and then completely restart. On the positive side, it was fairly easy to define various experiments because everything could be tweaked from inside this test function. In retrospect, there are two things I should have done. First, I should have created a separate test for each experiment. I could make them all pass by lowering my expectations, or I could let them fail, but this would document the experiments I had already done and which had passed or failed for anyone looking at this repository. Second, I should have factored out the optimizer, its parameters, the learning rate scheduler, the number of epochs, and even the data set. I should have factored those out into a training configuration. That way I could literally list in code the configurations that I know work and that I know do not work. Anyway, I'm going to leave that for a future video and focus now on transfer learning. First, let's create a couple of fast unit tests that test the model on the two data sets for just a single batch.
Let the code flow.
All right, that took about a minute, which is much better than what the full training takes. All I did here was, after the first batch of training, assert that the loss is within reason and then break out of the training. And the same thing here. After the first batch of training, assert that the loss is within reason and then break out of the training. Now let's try to accelerate the full training on the CFAR10 dataset by using transfer learning. In fulltraining.py, I'm going to copy the CFAR10 training test. But I want to pass a new parameter to my network initializer, saying that I want to transfer learn from the default pre-trained weights provided by the Torchvision library. Now let's make this interface a reality.
Let the code flow.
That completed transfer learning for 90 epochs in about 6 hours, significantly less than 9 for full training from scratch. Unfortunately, it still did not converge at the expected level of accuracy. My system also spontaneously restarted a few minutes after the test completed. I tried another experiment, this time lowering the learning rate a fourth time, but that didn't improve the final accuracy. I lowered my expectations for these training configurations and marked those tests as mediocre results. I did some searching on the internet, and the best final accuracy I have seen anyone achieve for this data set in this model is 83.7%, so I won't feel too bad. Here are the changes I made for transfer learning. If I want to get a model with pre-trained weights, I need to use this AlexNet function. instead of directly constructing an instance of the AlexNet class. Because of this, I've stopped subclassing the AlexNet class and instead assigned an instance of it to self.model. This is an example of preferring composition over inheritance. If transfer from is none, then we're training from scratch. So I instantiate AlexNet and replace its first layer, just like I was doing before. Otherwise, transfer from is assumed to specify a set of weights to use in acquiring a pre-trained model. The specified number of channels has to match the number of channels in the pre-trained model. If not, I raise an exception. Then I go through all the parameters of the model and mark them as not requiring gradient calculation. This ensures they won't be adjusted during training, but we do want to be able to train the layers near the output of the model, the classifier parameters. So I've copied the code from the constructor of Torchvision AlexNet to replace the frozen classifier layers with identical trainable ones. I'll push this code to the GitHub repository, and maybe someone else can find a training configuration that's more accurate on the CFAR10 dataset. I hope it doesn't force your computer to restart. In this episode, we discovered that AlexNet had been previously brought out of the wild in the Torchvision library. It's available for inference using weights trained on the ImageNet dataset. We adapted it and trained it from scratch on the MNIST dataset. Training it from scratch on the CFAR10 dataset posed a surprising number of data science problems and even a hardware crash, but we managed to get one test passing reliably. We then adapted the model further for transfer learning and significantly accelerated training on the CFAR10 dataset. The experience highlighted the value of having separate tests documenting each experiment, of having the training configuration in one place, and the potential value of factoring out a configuration object. Thanks so much for tuning into this episode. If you found it instructive or useful, please share it with others who might also. Don't forget to click the like and subscribe buttons, and I also welcome all of your constructive comments.